In this video, we are going to find positive integers x and y such that x cubed plus y cubed equals x squared plus 42xy plus y squared. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. We notice that for this equation, the left side sum of cubes is a polynomial of degree 3, or on the right, the polynomial is of degree 2. So there is some sort of imbalance over here. Our first step will be to try to balance the equation so that we are considering something that both sides of the equation, or equivalently some fraction for both the top and the bottom, have the same degree. So to do this, I'm going to first factorize the left side, which gives x plus y times x squared minus xy plus y squared, and the product equals to the sum of squares plus 42xy. Then moving x squared minus xy plus y squared to the right, we have this fraction. And we know that this fraction also has to be positive integers because x and y are both supposed to be positive integers, and the sum will clearly also be of the same nature. So this is a positive integer. Of course, this fraction can be somewhat simplified by doing some kind of long division. We can rewrite that as 1 plus 43xy over the same denominator. So this part will be the thing that we have to consider now. It's simpler because there's only one term at the top. So then I'm going to consider the greatest common divisor of x and y, which I'm going to call it d, which is a positive integer. Then let small x as this greatest common divisor times big X, and do similar things for y. So then big X and big Y are co-prime integers. Of course, they can be positive as well. Then for this fraction would become d times big X, d times big Y, and then over d times big X all squared minus d squared big X big Y plus d times big Y all squared. Then we can simplify this and we get a fraction of similar shape. It's just that small x and small y now becomes big X and big Y. And again, it's still supposed to be a positive integer. But now the difference is that we are now looking at co-prime positive integers big X and big Y. So notice that big X squared minus big X big Y plus big Y squared is co-prime with big X and big Y respectively, because there is always one term that does not involve one of x or one of y. But since, like for example, with x, when we compare with x, then when we have an extra y, big Y squared term over here, then we can't share any common prime factor with big X, because for any prime factor of big X, when we try to divide the other quadratic by this prime factor, then this y squared will always be in the way. And we have similar situation on big Y, where big X squared will just stop that quadratic to be a multiple of those prime factors. So since this quadratic has to be a factor of 43 times big X times big Y, but the blue part would not be a multiple of the quadratic, so the only possibility would be the denominator must be a factor of 43, and that gives very few choices because it can only either be 1 or 43. One more point to note is that this must be non-negative because I can rewrite this in this way. It's a perfect square plus a positive number times another perfect square, so it can't be negative. That means it can either be 1 or 43 only. Now to solve for big X and big Y, let's try each case separately. The first case would be if this quadratic is equal to 1, then I'm going to multiply both sides by 4, try to complete squares. Now if big Y is equal to 0, then that means the small y will also be 0, violating the condition that there will be positive integers, so big Y is at least 1, but that's the only possible option for big Y, because if y is even larger than 1, then this term will be larger than 4. So therefore, big Y equals 1, and 2 times big X minus Y equals plus or minus 1. And then solving, we have big X is either 1 or 0. Of course, we cross out 0. It's impossible. From this, we know that therefore, small x and small y have to be equal. And so, going back to the original fraction, we need this as positive integer. I can rewrite this as 43x squared over x squared, and that's 43. Now, x plus y has to be 1 plus this number, 43. So both x and y have to be 22. So that would be the solution when that quadratic equals 1. This is the first case. Now for the second case, when this equals 43, I can use a similar trick, which gives 2 times big X minus y all squared plus 3y squared equals 172. Now 3 times big Y squared must be at most 172. We can just try one by one, because big Y can only take values from 1 up to 7. So we have a finite number of choices. Trying big Y equals 1, then big X equals 7, or we just reverse it. Big Y equals 7 and big X equals 1. Then going back to small x and small y, for the left side we have 7d plus d, and then we have 1 plus 43 times d times 7d, all divided by 7d all squared minus 7d squared plus d squared. So simplifying, 8d equals 1 plus 301, all divided by 43, and that means d equals 1. So therefore, we have two more pairs of solutions, 7, 1 and 1, 7. And you can check, and they are both all valid. So together with 22 and 22, this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.